I've heard a lot about this motor power company from Italy. It seems it's very popular in Europe, and a lot of people have asked me, which motor should I get and how do I set it up. So I'm going to show you how to do that. I had difficulty finding motor power company because when you Google that, you do find a lot of motor power, but not what you're looking for. But these are the guys in Italy. They make a bunch of different motors, direct drives, linears, rotaries. I guess they're good quality. They've got a manufacturing place there in Italy. There's their logo, Motor Power Company. And one day we'll visit and we'll park our little car in the parking lot. So I looked on their webpage and found this TETRA COMPACT E, which is basically the motor that I've got here. TETRA COMPACT E. It's was a little challenging to locate the winding, but if you go TC-E space 60 space 2B, you can find the information about that motor there. 400 watt, very Japanese-ish way of talking about motor power. 1.27 Newton meters of continuous, 3,000 rated, 6,000 max, although you could go faster based on the back EMF if you got the rectified 230 volts. They do a good job of providing data, inductance and resistance. I see 12.5 or 12,5 is how you say it in European millihenries, 5.2, 5,2 ohms of resistance, Newton meters per amp and RMS, so you got to make sure you enter that right or convert it. Amps per RMS times the square root of 2, 1.414, 35 volts per krpm. You got your peak and continuous, your inertia, that's all good. I didn't want to take a peek at the feedback devices though. So I looked in the manual, feedback E1. I see they have incremental encoder. This is hyperphase. I don't like hyperphase, so I'm not going to recommend it. So I'm going to go for the proprietary 20-bit A2. I've got an A4 here, and there's an A6 with a battery. So here's how to connect the motor power based on what connector you have on the motor. UVW, protective earth if you have a brake, 0 to 24, no brake, military style connectors. I'm trying to zoom in on the feedback connector types, but here you see the E1 incremental encoder with Halls, differential A0, UVW. Just hook up the UVW, don't worry about the knots, +5 and ground. That's a normal voltage for a servo drive. Again, I'm not going to recommend the hyperphase. 7 to 12 volts. Wait, what, I need a 9-volt battery or something? Sine, cosine, plus data. I'm sure we can make that work, but it's going to be an effort. This A2 feedback connection is just data. You don't need a battery for single turn. It said 20-bit, but I got 23 bits out of this. I'll show you how to do that. Yep, some UVW cables. Should be a connection for the other feedback devices here. Yeah, so sine, cosine with 8 volts. I use 9 volts. That'll be fine. Incremental encoder with Halls. That's great. Clock and data. So that's like 20 bits. I said 23 bits and did a downshift. So I think I cracked the code on the proprietary. Smells a lot like a Tamagawa. There's that A1 again, hyperphase, 8 volts, crazy stuff. A2, 20 bits, A1, absolute. Anyways, we'll just keep it simple and we'll just wire clock and data, +5 and ground with a shield right to the feedback. You can see I've got the Xenus Compact. It's a 3 amp continuous 9 peak. It's well sized for this little motor. This is a higher voltage, lower current. UVW. There's an earth on the frame here, so the motor gets connected to earth, and there's no earth wire cable, so they saved a little cable. Feedback to minimum, saved a little cable. Nice braid on the outside of that, by the way. USB adapter to RJ11. I'm just going to use the CAN port here with the terminator. Node ID set to 1. I've got the stow bypass jumper installed here. 24 volt keep alive. If there's a break, you'd wire up the brake. There's no brake on this motor. So we're going to take a quick peek at how to do the setup on this thing so we can figure out this A4 encoder. So it's a brushless rotary motor, and it smells a lot like a Tamagawa. I put in 23-bit. If I put in 20-bit, I got some kind of error. I just used a downshift to get the resolution away from 8 million counts per rev at 100 revs per second. That's too many counts, gigahertz. So let's not go crazy. 19 bits, 524288 counts per rev should be fine to go over 6,000 RPM. Single turn, no battery. There's another A6 with a battery. Data. Multi-turn. So maybe multi-turn's 4096 with a battery. So they got that motor too. There's no feedback faults. If you have good cabling, grounding, shielding, don't ignore it. I put in some, decel ramps. If I had a brake, it takes a little while for the brake to kick in, but this is for an e-stop. I'm just going to do CAN mode here. Emulated feedback. If you had 8 million counts per rev and you want 100 revs per second, that's gigahertz. I got 524288 counts per rev, so that's still 50 megahertz. So divide by 4, you get something in the more normal range, like a 10 megahertz approximate. And that's for like emulating encoder output. Again, I just picked the data off the data sheet. There's an 8-pole motor. Has 4 electrical cycles or 4 pole positions. I can feel the motor stick when I do the manual phase, but inertia, peak and continuous. I put in a speed that's greater than the 6,000 because maybe I want to go 6,000 and I need to set my velocity limit just over that. There's the Newton meters per amp and amps RMS. There it is in peak. Volts per radians per second. I don't know if I believe the 35 volt. It's more like 42 volts per krpm. That's why the speed's limited to 3,000 RPM for rated. You can put in 35 volts per krpm. You put in whatever you want. It's not used for anything. It's just good to know the data. Inductance and resistance is used along with the torque constant and the torque to calculate the current. And whatever you put in here, it takes half of it for a good, safe start for limit. And then you can calculate the initial tuning parameters. With good data, things look pretty good. Check out the current loop bandwidth here. Turn the motor up, it made a lot of noise. Calculated values. Well, we'll tune this thing, but based on the data I put in, these are CP and CI. Nice odd numbers, so artificial intelligence calculated those for us. Velocity loop, so you can put in, you always want to have 10% higher than the fastest speed you'll ever go. So it's giving me a warning. It's like, no way, you can't go that fast. I'll just say okay to that, but that could be a safety limit. These are also calculated for the velocity loop. Defaults for position loop, if you had a large inertia, knock that down to 100. I just keep the feed forward constant. And you can tighten up the following error and tracking window later. So I'm going to go through the tuning real quick here. So for current loop, auto setup checkbox, picks what you want to look at, hit start. Here we go. Perfect square wave, commanded and actual. So I keep doubling until I get some ringing. That's pretty close here. So, wow, look at that. All right, cut it in half, and then we'll do 150 for that too. You know, we're not going crazy. We want about a kilohertz of current loop bandwidth, plus or minus 200 hertz. So goes out flat, rolls off. So I got nice round numbers, so you can tell the human tuned this. Ooh, that's a little high for current loop bandwidth. We'll see what we got there. Oh man, yeah, it's a little high. So I'm just going to knock it down a little bit. All right, and that should be fine. About a kilohertz plus or minus 200 hertz would be good. Let's open up the scope again, and we'll do velocity. That's 10% of the speed. I knocked this down. It was at 1,000, but if you have some load on there, you need to knock this acceleration down. Maybe 100 revs per second squared. Slow this frequency down. You don't want to bang back and forth too fast. If it's a 10-to-1 inertia, that's probably where you want to have it, a little bit less than that. So this is auto setup checkbox, velocity loop gains, not very stiff. I'm going to double till I get oscillations. There it is. All right, keep that thing from falling off the table here. So there's the gains too high. Again, you can tell I tuned it, nice round numbers. So I got a little ringing there. I'm going to make it a single pole at 200 hertz, and we'll try doubling it again. Look at that. So move the pole out, phase margin, and you crank up the gain. It's a little ringy. I'm going to leave it with the gain margin there. It's 600. Probably not a good idea to go to 1200 here. It should be stable. Maybe it's marginally stable. Whack it with a hammer. You might get oscillations. So I'm just going to leave the filter at a single pole. Stiffness is pretty good. This motor seems to need a little more integral to get to steady state. So we'll take a look at that. Yeah, there we go. Wow. All right, we might turn that back down when we tune the position loop. So we'll do a little 524-288, 10 rev move trajectory. Let's go 1,000. We tested the 500, so we can use that. This is 10 revs, and we're going to look at, looking at the wrong thing again. Auto setup checkbox, 524-288, 10 revs. And we'll take a look at, after the move, the settling time. That looks pretty good. And if your integrator was over integrating, you would see an overcompensation here at the end of the move. And if it was under integrating, yeah, so not quite enough there. Interesting that it's about the same as VP. Most of my motors don't tune up like that, but you got 19 bits of absolute single turn. If you had a large inertia, you'd want to cut that down to 100, like a 10-to-1 kind of ratio for inertia mismatch. Maybe lower if you have more than 10-to-1. But we don't have any inertia mismatch here, so we can crank up the proportion a little bit. Notice the steady state while you're moving is near 0 because, well, that's where it's at. Yeah, little hiccup in here on the way, but let's do 1,500. And yeah, that's some pretty awesome settling here. So a little S curve, and can round the edges a little bit here to get rid of the disturbance or the jerk in the system. So 10 times should be a little more rounded. Well, that's it.